Now please remember this, students, this is a comprehensive lecture that is covering almost every aspect that is required for your preparation for the chapter of oceanography. Are there mountains even taller than Mount Everest present? Yes, there are. That is why please remember that study of oceanography or the oceans is also very critical for your geography as well as the civil services preparation. Very often you can see in the PCS exams also this is being repeatedly asked. These number can be asked. They can ask you in the UPSC paper also. All the diagrams that I have presented here are made by hand. Every concept that is explained is again in detail so that you can very well appear in your prelims as well as the mains examination. Hello aspirants, welcome to PW OnlyIAS. I am Harpreet Singh with another lecture from the Physical Geography series of the NCERT. Now please remember, this is a very important lecture because we are going to cover the aspect of oceanography, and that means the study of the oceans in detail in this particular chapter. That is lecture number 12. Now please remember this, students, this is a comprehensive lecture that is covering almost every aspect that is required for your preparation for the chapter of oceanography. Now please remember this, all the diagrams that I have presented here are made by hand. Every concept that is explained is again in detail so that you can very well appear in your prelims as well as the mains examination using these concepts. So let us begin today's lecture. Now, before we begin, these are the UPSC foundation courses. Many students ask, sir, which are the paid batches? We want to enroll them in them so that we can get comprehensive prelims, mains and the interview guidance along with the various test series concept and a lot of other things. So over here you realize we have the crash course for 2026, those who are appearing for the preliminary examination. You have the Srijan prelims in English and Srijan prelims in Hindi for 2,999 rupees. 2 years, 2027. Sankalp, it is in English, Sankalp in Hindi, and Pinnacle. In this, like, we are completely going to teach in English. The Pinnacle batch is a 2-year comprehensive preparation for the prelims, mains and the interview completely in English for 13,499. Again, there's a flagship program that is a 3-year Praram program where it is specially for the college-going students, for those who are preparing for the civil services for 31,999. Let us begin today's lecture. Now, the lecture which we are going to deal along with the other lectures, you can find the PDFs of this in this particular Telegram group, along with details regarding anthropology optional, geography obviously, society and social justice and civil services preparation in general. You can also follow me on this Instagram account. You can connect to me on this also. So this is the link along with the name. Okay, when we're dealing with the oceanography, see, we are not studying that, oh, this is Pacific Ocean, this is Atlantic Ocean. We already know that. We've already done that. What we are going to deal is what it lies beneath that. Beneath, when we just go underground, under the water, what is it that is basically present there? Are there some kind of mountains present there? Are there some kind of canyons present there? What is present there is again a very important point of discussion for a mere reason that this is something that is not directly visible to us. Now, for example, if you're on the top of the land, let us say you are in Africa, you're in India, you're in Australia, the things, the vegetation, the animals that are present are easily visible to the naked eye. But something that is present deep inside is something that is beyond the reach of human beings also. That is why it raises a curiosity also. So what lies in the ocean floor? Or what type of life is present in the ocean floor? What form of landforms are present in the ocean floor? So what type of structures? Are there mountains even taller than Mount Everest present? Yes, there are. That is why, please remember, that study of oceanography or the oceans is also very critical for your geography as well as the civil services preparation. Now see, over here, a diagram, a map which we have already used multiple times that I have drawn by hand also. This is again, the parts in blue refer to the oceans and the green basically referring to the continents. Now see, certain observations which I'm going to tell you, we have done this part also earlier just to remind you these parts so that when we begin with the oceanography, you have certain things in mind. Water covers 70.8% of the surface while land only 29.2%. More than 75% land is in the northern hemisphere. Pacific Ocean occupies close to 1/3 of the surface area of the earth. North Pole is surrounded by water and the southern pole by land. Why? Because northern pole lies in the Arctic Sea. It is basically a sea that is frozen, while Antarctica is where you know that South Pole is located in Antarctica, and Antarctica is a continent, and that is why there is a land mass present there. Next, Continents roughly are triangular in shape except Antarctica and Australia. Now, this has also got to do with the plate tectonic movements and the movement of the continents, movement of the plates that have taken place, which have resulted in their shape being roughly triangular. Not all, as you see, Australia and Antarctica are not triangular in shape. But if you see other continents like North America, South America, the regions like, for example, Africa, they appear to be triangular in shape. So this is what is being said. A rough estimate, not exactly for every continent, but yes, you can be asked this statement in your preliminary examinations also. So these are rough guidelines which you already know about the oceans and the land. Now, when we begin with the ocean topography, now let us come to the topic that we're dealing with. This is ocean topography. When I talk about topography, a lot of things come into our mind, right? When I was talking about the land surface topography, in the topic of geomorphology, which we had done earlier, you would have seen that, sir, you had discussed about what type of landscape are present on the surface, what type of mountains are present, what type of plains are present, what other volcanoes present. So we have done all these things when we were studying the topic of geomorphology. Similarly, in the oceans also, you realize that ocean topography refers to the shape of the ocean floor and the subtle hills and the valleys on the sea surface. Now, what type of landforms or shapes are present in the surface are again an important consideration where we are studying in ocean topography. I've used the word bathymetry here. Why bathymetry? Please understand. What is bathymetry first of all? Bathymetry is a measurement of the ocean depth, charting the shapes of topography of the ocean floor. Now, bathymetry is a means through which we basically are trying to understand what is the depth of the ocean. What type of shapes means what type of landforms are present in the ocean floor. Are they tall? Are there deep trenches associated with them? Are there small hills? What is associated? What is present inside? That is what is being done by bathymetry. So bathymetry are ways in which the ocean topography is basically charted out or seen what type of topography is present. Now, the question arises, sir, how do we do it? Now, please remember, this methodology has evolved over the time and it is still evolving. It will depend upon the level of technology that we achieve. As the technology increases, we're going to have better methodologies in order to calculate and measure the ocean floor also. Now, earlier what used to happen, how we basically do it, see, measurement of the ocean depth and the shape. The common techniques. Now, first is, let us see, first is depth sounding. Now, depth sounding is one of the oldest methods that were used. Now it is not very accurate also, but what it involves is, let us assume you are moving, let us say there's a ship that is moving. They will extend a weight using a thread, let us say thread or a rope, using a thread. Now let us assume this, let's see, this is, let us say this is a weight, right? Over here is a weight, and this is being extended down. Now, when it touches the floor, we'll get to know that, okay, this is when touched. Then you start moving, and then possibly you calculate using that how much time it is taking to touch the floor. Let us say it has taken this much time. Now, you know the density of water, you know the density of the substance. It is going to take some time to reach the floor. By calculating that, you get to know that this is the possible depth. Okay, then after some time you will again move ahead and then you'll drop it here. Then you'll get to know, okay, this is the depth. So possibly if this is the type of landscape that is present, let us say there's a depth and there's a hill. So if a ship is over here, it has dropped this, it has gone down. It's just taken some more time. Over here it will take less time. So you know that there is some sort of hill that is present here. Using these repeatedly dropping a rope with a weight, and you are calculating the time it is taking to reach the floor. Using that, it is basically being calculated. This is known as depth sounding. Throwing a weighted rope from a ship and recording the time. This is a highly inaccurate method because you can get to know that this particular point, the time is more or less, but you cannot chart out a proper topography that is present deep within the earth, deep within the ocean floor. Then came the echo sounders. Now, echo sounders basically use the sonar techniques, right? Now, what happens over here is sound waves are sent from the ship and detected by the receiver. Let us take it again. See, let us understand this again. Supposingly, there's a ship here. It sends sound waves. Now, this is a surface. This is an ocean floor. The sound waves go there and come back, right? We know the distance because the time it is required, and we know the speed of sound also. So, based on that, we get to know what type of ocean topography is present there. Now, sonar is again a very effective methodology and a much more improved form than over the depth sounding methodologies. Now, in spite of this, you realize it is very difficult to map the ocean floor properly using sonar also, because it is a very time consuming method. It might not cover every aspect. So that is why we have even better technologies. Satellite altimetry. Now, the satellite altimetry basically uses radars and laser altimeter, which basically use the pulse electromagnetic radiations in order to know what type of topography is lying. Now, these are again advanced technologies through which you get to know the exact possible details that are present inside the ocean floor, or in the ocean, what type of landscapes are present. That is why these techniques, again, this can be asked in your examination also, in your mains as well as your prelims examination. So these are the important techniques which are used as means of bathymetric techniques. Because see, seafloor spreading and all we have done. We have done the aspect when we were doing plate tectonics. So these are now advanced concepts that you are doing in the topic of oceanography. Let's move ahead. Having studied that what type of methods are used, we will now get to know that based on these measurements, methods and techniques, that we have found what type of landforms are present inside the oceans. There are various categorizations in which we have divided. Some of them are the major oceanic landforms and relief features, some the minor. So let us say the major ones first. This is a diagram that I have made using hand. This is a continental crust and this is an oceanic crust, just for a representation purpose. And there are a lot of depositions also that take place here. Now, please remember this part, first part, we will be studying each and everything over here. Don't need to worry about that. This part is known as the continental shelf. Now, this continental shelf basically lies beneath the water only, but it is very shallow. It will vary from place to place, but it is generally shallow, or most shallow part with respect to the complete ocean, because as you move ahead, the depth will increase. Then you have this slope that is present after the continental shelf. This is known as a continental break. This part is known as continental break. We'll see that. This is known as a continental slope, where a rapid decrease, in the, a very steep slope is present. So rapid decrease in the depth is very often seen here. This is continental slope. So the slope is the gradient is really very high. Then you have again this part, which is known as a continental rise. The slope is not very steep here. After that lies a very uniform plain, which is known as an abyssal plain or deep ocean plain. And also one more ingredient which is not present here, which you'll see the diagram, are the trenches. The trenches that are present, right? So along with these, continental shelf, continental slope, continental rise, abyssal plain, and the last being the trenches, form the major oceanic relief features. You should keep in mind, in the examination, you can be asked, which among the following are the major oceanic relief features? So you should please remember that the NCERT mentions about these and the trenches. So those are the ones which lie under this category. Let us study each one of them now. You know, this is the continental shelf, right? This part. Now let us see what is the continental shelf. It extends. It is the extended margin. It is the extended margin of each continent occupied by relatively shallow seas and gulf. Now you know that very well. These are again the extended margin. This is the continental crust, extended margins of the continent. Now these again are underwater. Now it might be a little bit shallow in the form of, let us say, shallow seas might be present, some gulf might be present. It is a shallowest part of the ocean, showing an average gradient of 1 degree or even less. So as you know that as you move ahead into the deep ocean, you will realize that the gradient obviously will vary, but the depth will definitely increase. Because over here, you know, it is first of all shallow, the gradient is not very steep. Why? See, till here the gradient is less. After that, when you move ahead, the gradient will rise because the slope is steep here. The slope is not steep here. That is why if you see, the gradient is of 1 degree or even less. Then you have, this typically ends at a very steep slope called the continental shelf break. Now see here, this particular point where the continental shelf ends and the continental slope begins is known as the shelf break. So we can put it over here also, shelf break, right? This particular point. Then the average width is about 80 kilometers. Now it varies place to place. So it is almost absent or very narrow along the margins of the coast of Chile and the coast of Sumatra. So over here you realize that it is almost absent, it is not present. While in the other regions you will realize that in Siberia or Arctic Ocean regions, it is up to 1500 kilometers. So it can be very huge. So it will vary from place to place. Depth also varies. Now very often you will say that, sir, you said these are the shallowest parts. Does it mean that it is very shallow? Now again it will vary. See, over here the depth can be few meters to even in the distance of 600 meters also. From 30 meters to 600 meters. Now this is again 600 meters itself is huge, but again it is still the shallowest part. As you move ahead into the deep seas, you will see the depth will definitely keep on increasing. So the average depth of this particular part also varies, right? Now let's come to the next part, that is continental slope. After continental shelf, there is a break. That break basically is again pointing to the rapid or a very sharp gradient, which is represented by continental slope. Earlier it was shelf. It connects the continental shelf and the ocean basins. It begins with the bottom of the continental shelf and sharply drops, and there is a steep slope. So there is a very steep slope that is being marked in this. Very steep. Now the gradient or the slope of the slope varies from 2 degree to 5 degrees. Now 2 degree to 5 degrees, again very steep with respect to this ocean topography. We have already seen that the continental shelf are 1 degree or even less than 1 degree. But with respect to the continental slope over here, you guys see that the gradient is 2 degrees to even 5 degrees, in some cases even more. So the gradient that is really high, that means the slope is very steep. The depth of the slope region varies between 200 meters to 3000 meters. Again, it varies place to place. It can vary from 200 meters to even 3000 meters. The slope boundary indicates the end of the continent. Now please see. Sometimes it is written that continental slope marks the end of the continent. Please understand why. Now many will say, sir, you've already mentioned continental rise here. So how can this be marked as a continental end? Or over here you have written that it connects the continental shelf and the ocean basins. Why have you not written that it connects the continental shelf and the continental rise? These two issues might have come in your mind. You would have observed that. The reason behind it is, please remember, this continental rise that is present here is not present everywhere. It depends upon the supply of the sediments that is brought by a lot of rivers and other remains. So sometimes what happens is, if the continental rise is not very clearly visible, it is considered a part of the continental slope only. So in NCERT, if it writes that the continental slope connects the continental shelf with the plain, this plane, it is not wrong. If they had written even it connects the continental shelf with the continental rise, then also it is correct. So both the statements are correct. There is nothing wrong in that. When I have written here, it indicates the end of the continent. Yes, because various books consider continental rise as a part of continental slope. So that is why these statements are written. So it is not wrong. In either case, it is correct. Clear? Okay. Canyons and trenches are observed in these regions. We will see what submarine canyons are, what trenches are. These are also observed in this particular region. Okay. Continental rise. Now you see, post the continental slope, you have this continental rise present. It does not have a steep slope, right? It is a type of seafloor feature that consists of gentle slope of sediments from deep oceans to the continental floors. Now please understand that the sediments are basically carried by the rivers and the streams, which are basically deposited then in the oceans. And more the supply of the sediments are, then there will be possible presence of the continental rise also. If it is not present, there is a lesser chances, and possibly continental slope or major extension of that is considered, or it is considered a part of the continental slope in that case, if the sediment supply is relatively less. It merges with the abyssal plains, common in regions where there is sediment supply is large. Now please understand that is why, if let us say a river is coming from here and a lot of supply is being there from the sediments, possibly you can see a continental rise here. If it is less, possibly you can just see this continental slope extending. There will be no specific features like continental rise in that case. It is possible. That is why sometimes continental slope is shown in the diagram, but continental rise is not shown. It is because it might not be present everywhere, right? So this is again continental rise, but you have to mention in an examinations, right, that continental rise is present. Deep sea plains. Now, if you see, move ahead, then there is this flat plain, right, above the continental crust. Now see, this plain basically refers to the deep sea plain. Now, this plain is why? Because see, again, this is referring to the oceanic crust, sorry, the oceanic crust. On top of the oceanic crust, you have a lot of depositions might have taken place. Now, see, large number of plants are decomposing, large number of animals with respect to fishes and all are dying. Lot of calcareous remains, siliceous remains, other biogenic and non-biogenic substances are basically falling on at the bottom level, and that leads to a lot of deposition be taking place, right? As you go in the deeper level, you will see more of silica, siliceous remains more, less of calcareous. That is also true. We'll understand that when we are doing the ocean deposits. Now see, abyssal plain are the underwater plains of the deep ocean floor. The depth might be from 3,000 to 6,000 meters or even more. They are flat areas of the ocean floor with a gradient well below 0.1 degree. The important thing is the gradient is well below 0.1 degrees. Why? Because these are very flat plains. Obviously, there will be some relief features, but these are plains these are very flat in nature. They are formed by the spreading of the ocean floor and melting of the oceanic crust. Now see, you know that very well that we have already done in the plate tectonics chapter that the oceanic crust is basically an outcome of the spreading of the ocean floor. As this ocean floor spreads, you know that fresh magma comes out in the form of lava and it is deposited, and you have the mid-oceanic ridge in between, and this keeps on moving because if this is a constructive plate boundary, over here this side is going to be destructive plate boundary. That means over here the crust is being destroyed. Yes. So the oceanic crust is relatively newer in nature. It is young in nature. We've already done that. Similarly, there will be a lot of depositions taking place also in the form of some sediments, in form of certain animal remains with respect to siliceous remains, a lot of stuff. So that basically forms the deep sea plain. Now, they are flattened and smoothed regions and covered by marine deposits. As I told you, marine deposits basically cover it. That basically forms the integral part of the deep sea plains or the abyssal plains. Now, this is again the representation. Now, let us see the oceanic trenches. Over here, the diagram is showing you a trench, but it does not show you how it is formed, which I'll tell you now. Please see. Do you see here? You have seen this is the continent part. This is the continental shelf. This is continental slope. This is continental rise. The flatter part is known as the abyssal plain. You might have small hills like the abyssal hill. Then you have the sea mount. We'll also study this. You have some volcanic island here. And then you have these great depths over here. These are referred to as the ocean trenches. These are the deepest part of the ocean. Now the question arises, sir, you have shown this, but how are they formed? If you remember, when I was telling you about the seafloor spreading, I had shown you that trenches are very often found at the destructive plate boundaries, that is the converging plates. Let us see the diagram. Now see here, this is the ridge, mid-oceanic ridge. This is, let us say, the plate that is moving. This is a plate under which it is subducting. Now see here, very well, very nicely see it. Supposingly, there are two plates, and you know that very well the plate which is denser in nature is going to subduct, right? The plate which is denser in nature is going to move down. This is let us assume this is the oceanic crust. This is the continental crust. This oceanic crust is moving. It moves down like this. See this? Do you realize from this particular let us see this. Now see this in this manner. Do you realize from this particular point there is a decrease in height rapidly? If you're moving here, you see here it is rapid fall in height. This is what is a trench here. If you are moving in this region, if you see, oh, there is such a deep height, it can be various kilometers also. This is what is a trench. Why? Because the subduction in taking place here. See here, this plate is moving down here. So this particular part, the depth is more. So this part is known as trench. Now, it will depend upon the nature of the plate. It depends upon the nature of the region. You can realize the trenches can be very deep also, like the marine trench. It is very huge and very deep. So these are how trenches are formed. These are formed at where there is converging plate boundaries or destructive plate boundaries, because this plate boundary is being destroyed. So over here you will find the trenches. The ridges are found on those regions where there is divergence or constructive plate boundaries. We have already done this in the plate tectonics, so let's move ahead. Move back again. Trenches. So these are the deepest parts. So these are the deepest part, right? The trenches are relatively steep-sided and narrow basins. So why? These are, you see, these are very steep-sided and again narrow also. They're not huge. They are huge with perspectives to human being, but with respect to the plates and all, they are not that huge. Right? They are some 3 to 5 kilometers deeper than the surrounding ocean floor. They are formed due to the subduction of one tectonic plate beneath the another. You've already seen this. So one plate is subducting under the another continent, another plate. The one which is more denser in nature is going to subduct. Please remember, oceanic plates are more denser or much more denser than the continental plates. One fact. So that means, I know that we've already told you the plates which are more denser in nature are the ones which are going to subduct. First. Second, if there are two continental plates or two oceanic plates, you will say which one is going to subduct? Again, the one which is more denser is going to subduct. Clear? So that is something you should know. Now over here, when we see the oceanic plate and the continental plate which are basically converging, the continental plate is lighter, less denser. So the oceanic plate is going to subduct or move down. Clear? Okay. So they are large in number using the NCERT facts also. NCERT mentions that there are 32 in Pacific Ocean, they are 19 in the Atlantic Ocean, and there are 6 in the Indian Ocean. So these are again very often you can see in the PCS exams also, this is being repeatedly asked. These number can be asked, they can ask you in the UPSC paper also. Nobody can restrict them. So you should know because these are various important NCERT facts also. So please note it down. Okay. What we have done are the major oceanic relief features. Now these are the minor oceanic relief features. Let's see them. First, seamount. Can you see this seamount? Yes, there are a lot of phenomena, a lot of processes through which it can be formed. There is no one method or one technique or one, let us say, phenomena. But let's see. So these are like small mountains which do not have a flat top. These are basically volcanic origin. It is a mountain with a pointed summit. It can, see, there are two ways. Either it can be like this, it is not flat, or it can be pointed also. Both ways it can happen. But it is not plain or flat. So it is a mountain with a pointed summit rising from the seafloor and does not reach the surface. The important feature is that it does not reach the surface. It is underwater. They are of volcanic origin, possibly because of the volcanic eruptions. Hotspot activities also can lead to the formation. They are 3,000 to 4,000 meter tall. 4,500. These are again tall, but they do not reach the surface. Now, what are the possible methodologies through which it can be formed? We have already studied the hotspot activities and the mantle plume. So you know the phenomena behind it. So often they are from the volcanic activities associated with the hotspot. So because of the hotspot activities, some type of this volcanic origin structure might be formed, but it is not so tall enough to reach the surface. One. Also formed due to submergence, due to erosion, or due to sea level changes associated with a volcanic island. So it is one. Another phenomena can be that it was like this island, like a volcanic island was present, and a lot of erosion took place, and due to the erosion, the height decreased. One, that is possibility. Or there was submergence of the continental landmass. Due to the submergence, it has moved down. So these are also a way through which this seamount can be found. Clear? Okay, now this is one feature. Another is goyots. Goyots are completely same as seamount. The only difference is it has a flat top. It is a flat-topped seamount showing evidence of gradual subsidence through stages to become flat-topped submerged mountains. So, goyots simply mean that these are submerged, flat-topped seamounts rather than having a pointed edge or a crooked edge. They are simply flat. These flat mountains are known as the goyots. Next comes the submarine canyons. It's a very interesting feature. Now see very well, this part is referring to as the continental shelf. This part is referring to as a continental slope. And this part is referred to as a continental rise. I've shown you through a different type of a diagram. Again, handmade. So please understand this very well. When you see the Grand Canyon where the Colorado River is flowing, do you realize huge structures that are formed? And you just imagine the scale of water erosion that has taken place through these thousands of years and the power of the river erosion. And you see such tall type of structures have been found because of the erosional activity that has taken place over these thousands and thousands of years. So over there you see those canyons have been found due to the erosion. Similarly, you realize that there are canyons like structures that are found underwater also. They are not found everywhere, but in large places. Now what happens is there are a lot of phenomena through which it can be formed. Some say that it is possibly because when the rivers are bringing the sediments, a lot of pressure might be exerted, so they might form, due to the density differences, they might form some canyons, that is said. Sometimes they say that it is formed by the tides that come. Sometimes it is from that continental ocean currents also play a very important role. So sometimes it is said that the turbidity currents might be responsible for the formation. So a lot of phenomena are there. Again, if you're doing geography optional, possibly you go to the theories, otherwise it is not required. So whatever I've said, these points are one of the reasons, various reasons responsible for the formation of the canyons. So what happens initially in the pre-canyon phase, let us say there is some form of structure, or let us say removal of the continental slope might be formed. Why? Because sometimes what happens, let us say some currents that have come, that deep water currents might be present. Let us say there is upwelling that is taking place. Please understand, there might be upwelling of water. Do you realize upwelling? Sometimes what happens is, if on the top of the surface, please see here, the top of the surface, if we'll see in the ocean current chapter, if the river, let us say, let's see this. Let us say this is again the region of continental shelf and slope. Due to the flowing of the rivers, it is possible that the ocean water is piled up here. Water is pulled in this side, it is piled up here. So what happens is water will move down. This is known as downwelling. Water sometimes, deep underwater ocean currents also might lead to just their movement, and they might lead to these type of structures being formed. That is also possible. And then they will rise up. So when you see or talk about the ocean currents which you see about Gulf Stream, North Atlantic Drift and all these, Agulhas current and all, these are surface level currents. You have deep water currents also. So those deep water currents might basically be one of the reasons for the formation of these canyons. Again, these are one of the theories. There might be these deep ocean currents, there might be turbidity currents, there might be even sometimes tides are also made to be responsible for that. It is also said that the sediments brought by the rivers due to the erosion activities might also be responsible for that. So there are multiple reasons behind it. So what we see over here is initially little bit of, let us say, scratching of the ocean continental slope takes place. This might further enlarge, two of them might be formed. Then further the depth increases and you see the size of the canyon also increases. Now this is a process that takes place in a very long period, not a very short period. Similarly, then after that, a hook-like structure might be formed, and later on you see a very huge canyon might be formed, which is extending to the continental shelf, continental slope and continental rise. In the examination, you can be asked that the submarine canyons are found in which among the following features? Continental shelf, continental rise, continental slope. All of them. All of them. But the question might be asked that among these three options, where there is a greatest possibility of the submarine canyon be found, it is at the continental slope. Why? Why? The reason is the steepness of the slope. If you ever see the diagram, here, let's see the diagram. If let us say a deep sea current is moving, it is very steep, so it is not very steep, it might not lead to massive erosional activity over here. But this is very steep, so what happens? It is more resistant to the movement of some, let us say, deep ocean current. That is also one of the reasons. That is why the possibility of the submarine canyon to be present more in the region or start in the region is the continental shelf, continental slope rather than shelf or the rise. Obviously, when that size increases, you will realize that it will spread to the other regions also. So you have seen this, right? Okay, let's move ahead. Let's move ahead. They are like deep valleys comparable to Grand Canyons. They are found cutting down the continental shelf, slopes, and rise. Okay, let's move ahead. We've studied a lot on that. Now let's see an atoll, something very interesting. This is an atoll. You see, these are the coral deposits and you have a lagoon. So let us see. Atoll is a ring-shaped coral reef that encloses a lagoon in the middle of an ocean basin. So it is what? A ring-like structure with there's a lagoon in between them where the depth is not very high, or let us say the depth is not much. So there's a lagoon which is being enclosed like this. Like there might be islands surrounding this and there's a lagoon in between. Obviously the ocean is on the side. Now this is generally a ring-like structure if you see from the top. Now this is an atoll. Now how it is formed, let us see this. These are low islands found in the tropical oceans consisting of coral reef surrounding a central depression. This is another definition. Better definition is this one which you can use. How it is formed. Before we study the formation, you should have a little bit idea about the coral reef, right? Now the coral reefs are underwater structures made of the calcium carbonate skeleton produced by tiny animals called corals. Now these are the deposits that happen. That is why the coral reefs are found, because of the calcareous or the calcium carbonate depositions that are produced by the corals. Now see, initially what happens, there is stage. This is stage 1. Stage, let us write it, stage 1. Stage 1, supposing there is an island. Now this is the water level, right? This is the part which is above it is like an island. Now surrounding, just close to it, you have certain reef formation that is taking place. Now it might be completely joining this island, or there might be some depression or some small form of lagoon that is there, depends, right? So this is known as a fringing reef. Grows directly from the shore, located very close to the land. So it is located very close, just close to them, the island. This is known as a fringing reef. The next stage that happens is, this is stage 2. In stage 2, what do you see? In stage 2, what do you see? This island has relatively moved down, or in a way there is submergence of land. Now this can happen through two methods. Either this stage can come if there is submergence of land, one, or there is rise in the water level. In both the cases this can happen. You see this? Supposingly this was an island, if I say the water level rises to this level, so automatically you will have the increase in the ocean, because see, the coral reefs cannot be in deep sea water, right? Those are different types of corals. We're talking about these corals. So obviously there will be more deposition and rise, or there is fall in the or submergence of the island, then also this can happen. So in both the cases it can work. How will the stages proceed? Either there is rise in the sea level, or second can be where there is submergence of the land or the continent. In that case also the second stage or the future stages can come. So in this case you realize that this is a coral reef which is again created. It has water enclosed in them, but the island is also visible. So extensive linear reefs complex that are parallel to the shore, separated by a lagoon. So these are parallel. These reefs are parallel to the shore, but the island is also visible, and there's a lagoon over here. So this is known as a barrier reef. Now third stage is stage 3. Now this is not a tool as such. This is a tool forming stage, where you realize that again the third stage will come. Either there is further submergence or the further increase in the water level. In that case, further the coral reef will further expand, right? So this again the stage will again have the lagoon, but the coral reefs has further increased in size. Last stage comes where either there is rapid rise in water level further, or further submergence. In both the cases you see this island which was earlier visible has gone down, and this is covered by what? The reef. Now what has remaining is, now it is a ring-like structure will be there. If you see from the top, you will possibly see like this. Right? This is the top view, and you will have the lagoon here. This is the form of lagoon here. So last will be again the ring-shaped coral reef that encloses a lagoon in the middle of an ocean. Example is Maldives. Now, Maldives is a representation of a tool. Clear? So these are again handmade diagrams. If the question comes very repeatedly, very often these questions are asked, and when you use them, please remember that this is very, very useful for your preparation. You can make these diagrams by hand. Clear? Okay, let's move ahead. Mid-oceanic ridges. Now this is something we've already done in the geomorphology also. You know that very well. The mid-oceanic ridges is not simply that is mid-oceanic ridge is not confined to the Atlantic Ocean. It is present in various oceans also. It is basically formed at the regions where the divergence of the continental plates takes place. So as you have already seen that if there are two plates which are diverging, when the divergence takes place, again the magma basically is coming out. Magma is basically coming out. Magma comes out, that leads to the formation of some ridge-like structure. That is very long because the plate is very huge where the divergence is taking place. So that ridge again is formed. Slowly, the mountain that was formed. Let us say this is a boundary where this ridge is formed. Slowly, you realize this will move apart. Why? Because the plates are moving. Then new ridge will come here, new ridge will come here, new ridge will come here, while this will be moving apart. Similarly, let's see. Supposing this ridge is formed here. Now you know slowly this ridge. Over here also you can see small ridges. Why? Because earlier they were located here. Slowly they have moved this side. And further the erosion is taking place, right? So you see that this is a region where the convectional currents are basically moving. That is why you realize that the plate is subducting under the another plate because it is more dense. And the magma that is coming out in the form of lava is being deposited here, that is leading to a formation of a ridge-like structure which is known as a mid-oceanic ridge. So mid-oceanic ridge is a continuous mountain range spans across the entire ocean floor connecting different ocean basins. Why it is across so many continents, so many oceans? Because it is associated with the diverging plate boundaries. Now it is present in various oceans. So where it is present, you will see such structures being formed depending upon the scale, depending upon the level of movement that is taking place, and all that will basically be impacting the size of the mountain ridge. The most developed is obviously in the Atlantic Ocean. It is associated with divergent plate boundaries. You have already seen. What is divergent plate boundaries? This is what? Divergent. That means constructive. So this is what? Divergent plate boundaries. Divergent plate boundary. It is diverging. Over here you will have this mid-oceanic ridge. Clear? Okay. You know that very well. I'll not repeat it again. The evidence behind is we have done in the seafloor spreading that there is alternative bands of polarity that is present, right? This is a region where the ridge is being formed. You know that when the magma comes out, obviously when the magma is coming out, in that particular case, you know that it has a lot of magnetic substances, material in the form of iron, let us say. Now, when it comes out, the polarity of the Earth basically leads to the arrangement of the particles in the direction of the magnetism. What is the magnetic direction? Which is a north pole, which is a south pole, which is the magnetic north pole, which is a magnetic south pole. Based on that, the minerals are also arranged at the atomic level. So, we repeatedly see that because the magnetism of the Earth is caused by the convectional currents which is going on inside the mantle. Obviously, core is also involved in that, but majorly mantle. So, if there is the reversal in the direction of the convectional currents, it can lead to reversal in the polarity also. And this has happened repeatedly over centuries, multiple centuries. So when this deposition is taking place, we realize there is reversal in the polarity taking place on the either side of the oceanic bed, on the either side of the mid-oceanic ridge, and they are equally apart. Like this is apart, like this have the similar polarity, they have a similar polarity, this has a similar polarity. Why? Because possibly they both are moving apart. Why they have a similar age of rock? Because possibly they came out at the similar time. Possibly they were inclined at a magnetism which the polarity which the Earth had during that time. And this was basically measured based on the reversal of the polarity that took place within the Earth also. And it was calculated, yes, supposingly this has reached this position. Let us say it has reached from this position to this position in, let us say, a few thousands of years. And when it was calculated using a lot of techniques, it was found, yes, there's a possibility that in these thousands of years ago, there was reversal in polarity also that took place. So this basically helped us that the sea is also expanding or moving from this constructive plate boundary. And yes, we know that the mid-oceanic ridges is present here. So this we have already done in the plate tectonics. So just a quick reminder, that is why we know these mid-oceanic ridge concept is very closely associated with the seafloor spreading concept, which we study. Now see, like the crustal material are spreading from mid-oceanic ridges and the floor is moving on either side is called the seafloor spreading. We've already done this. Okay, temperature of the ocean water. Now this is again a very, very important concept. Temperature. Let's see them and study them. These are questions which are very often asked in your examinations also. So you should be very well aware of this. Let's see. First is what the factors influencing ocean temperature. First is latitude. Now if you see this, see, if the amount of temperature that is reaching, the amount of heat that is reaching the Earth will vary with respect to the latitude. The ones which are close to the equator receive the sunlight throughout the year. The ones which are in the high latitude receive relatively lesser insolation. Yes. Now see, latitude, the average surface water temperature. Surface, please remember, we are not talking about the deep ocean level. Surface water temperature of the ocean is 27 degrees Celsius. Now, as we move to the higher latitudes, we see a decrease in the temperature. Keeping other factors constant right now, the decrease is about 0.5 degrees Celsius per latitude. As we move from 0 degree, that is equator, to the poles. So there is a decrease as you move from one latitude to another. An estimation, average estimation has been done that is a decrease of 0.5 degrees Celsius. Now, this is how the latitude over here is also impacting it. Clear? Second comes the ocean currents. Now, if you see, ocean currents, again, we will be doing this chapter also. The warm ocean currents from the equatorial region carry warm water to the higher latitudes, whereas the cold currents basically bring cold water from the high latitudes to the lower latitudes. So, the warm currents and the cold currents are again responsible for changing the temperature also. For example, the Gulf Stream, which is flowing northward and then later on in the form of North Atlantic Drift, is basically responsible for increasing the temperature of the regions close to the Scandinavian countries, right? And those regions you realize are generally very close to the, again in the higher latitudes, should be frozen during the winter time, but they aren't. Why? Because the North Atlantic Drift increases the temperature of the oceanic region over there in the Northern Atlantic region, and it does not allow the region to freeze completely. So the ocean currents, again, warm currents moving to a region, to any region, increase the temperature. In simple words, while cold currents will decrease, vice versa for cold currents, I just now told you an example for the warm current. Let us take an example of the cold current. You know the Labrador current. The Labrador current, when it is moving along the Greenland region, then when it moves down, it comes close to the New York region. Now, New York region is, again, you realize, experiences this current, and it is so cold current. That is why during the winter season, very often the harbors are completely frozen. On the other hand, the Scandinavian countries which are at a higher latitude does not have the harbors frozen because of the North Atlantic Drift, which we will see. These currents names which I am taking right now, might be something very confusing that people will be saying, sir, what type of names you are taking? Let me give you just a hint of it before I actually do it. See here, the ones in blue are cold currents, the ones in red are in warm current. So the Gulf Stream moving here, it moves further in the form of North Atlantic Drift. So this region does not have a frozen winter completely at the frozen coast. Why? Because these are warm currents. The Labrador current which is coming, which basically moves down, and it basically leads to this the New York region being completely frozen during the time of winters. So this is how it impacts. Even if you see the Peru current or the Humboldt current which is coming to the region of the South America, you realize you have the Patagonian desert over here, which is a cold desert. It is because of the Peruvian or the Humboldt current that is present here. Similarly, whatever regions you see over here, like the Benguela current is also responsible for the arid conditions in the African region. Please see, these currents are very critical in the temperature of the regions or the surrounding land masses also, right? So just that was a simple representation. We'll be doing it after some time. Next is the prevailing wind. Now prevailing wind, please remember, are again very, very critical. As you see the winds that are moving, right? Let's take an example. Winds are one of the major forces through which the ocean currents are created, right? Because if you see the permanent winds that are flowing in the form of westerlies, the easterlies and all, you see the ocean currents are also following the direction. So the prevailing winds are one of those winds which basically help in the movement of the water also. These winds basically again help in the spreading of the temperature of the region also, directly also, indirectly also. So because when the winds are flowing, they basically there is friction existing between the water surface and the wind, and they try to drag the surface of the water, and that again leads to the distribution of the water also, a temperature distribution. So help in temperature distribution in the direction of the distribution in the direction of the wind. Land and mass. Let us see this. If you see the temperature of the northern hemispheric oceans is more than the southern oceans. Let us take the example of any ocean. Let us take the example of Northern Atlantic Ocean, and you take the example of the Southern Ocean. You will realize that the temperature, let us take the average temperature. Average temperature of the Northern Ocean, Northern Hemisphere oceans is more than the Southern Hemisphere oceans. Why? Because there is more landmass associated with the Northern Hemisphere. Now the land is also getting heated, it's going to give heat to the oceans also. So the temperature will increase. So that is why if you realize that in Northern Hemisphere, the temperature of the ocean is more, as more land is there, right? Next, the axial tilt. What do you mean by axial tilt? It is the tilted axis of the earth. Now you know that very well. The region which is experiencing or getting more insolation is going to be more heated. Yes? The tilted axis of the earth basically leads to certain regions receiving more light, more insolation. So that means axial tilt basically leads to certain regions receiving more heat. So if they receive more heat, the temperature is going to be more. Which are, now see, during that time when if the axial tilt is this way, this particular region will be experiencing more insolation rather than the southern hemisphere. Similarly, the axial tilt helps in the distribution of heat also, because sometimes the northern hemisphere is receiving more heat, sometimes the southern hemisphere. That is the reason. So it basically helps in varying amount of insolation, and thus more insolation, more is the heat, greater is the temperature. Upwelling and downwelling. Now please see, these two concepts are very important. Let me just show you this here. let's see here. I've already explained you this. Let us still consider it. Let us assume that there is this surface, this is surface water, right? As you move down, these are like deep, this is the deep plane, right? Now, if I say that there is prevailing wind, just take an example of it. Prevailing wind or some wind that is going on. Now, if you see this, this is the original level. This is the original level. Now, the winds are original level before winds. Before wind. Now, when the winds are flowing, there is quite a possibility, let's see this, there is quite a possibility that the wind is dragging the surface water towards the direction in which it is moving, right? Just imagine, let's take this example. Let me bring you a paper. Supposing this is a paper, right? If the certain winds are flowing, possibly it might move this in this direction. Yes. Similarly is done with the case of the water also, at least the ones in the top layers. So what can happen is, slowly what will happen, the level over here might move down and the level over here might increase. I'm just exaggerating, it is not so, but yet to a certain extent, yes. Now see, because why? It is moving in this direction, so it will pile up. This is known as the piling effect, piling. So water over here, now this is the new level. It is not a permanent feature. It is because the wind is flowing, that is why it is happening, right? New level due to wind. Now this phenomena that has taken place, it is known as the water is piled here. What is it? Water is piled here. Water is piled here. Now water being piled, so what happens is, the amount of weight this particular column of water is experiencing is much more than this. Why? Because there is more piling effect here. So what happens is, this lead to water sinking. This might lead to water sinking. Why is it sinking? Because it has to balance the effect. Now, please remember one thing. When the water is flowing, do you realize when it is moving or piling up, what has happened? There might be this might be the what? The ocean currents. This might be the surface ocean currents. That is why this is a movement like these are like the rivers in the ocean. When certain water is moving here in the direction of the wind, you realize like these are ocean currents, like the rivers in the ocean, right? So that is what is piling. That is why this piling has taken place. Now, because this is creating a lot of weight, this will lead to water moving down. Yes. Now what happens is, because this is a temporary factor, this has to balance it. This movement of water down, this is known as, downwelling. Now what happens is, over here you realize that now water which has sinked, you will realize the water which is present here will try to rise because this has sinked. Now again this will rise to balance it. So this water has to rise, right? Now this water will move to take its place. So you can see it in the form. This is moving to take its place. This is known as upwelling, where the cold water from the lower region is rising up to take the place which has been displaced by the ocean current or the winds which is moving. So this is what upwelling. Upwelling. The important dimension over here is, what do you understand? When there are surface currents that are moving, there is a reverse direction current which is flowing to balance that, and these are known as deep oceanic currents. These are known as deep oceanic currents, which are close to the bottom level or the low, at the almost the base level of the oceans, while these are the surface currents which are moving. This is the concept of downwelling. This is the concept of upwelling in order to balance the whole phenomena. So we have already done here. Please turn over, right? Clear? Upwelling and downwelling. Next comes the special variations. Now please understand, these are special variations, especially with respect to the nature. Let us say landlocked place, landlocked sea. Example, Mediterranean Sea. Mediterranean Sea has a higher temperature. Higher temperature. Why? Because it is landlocked. Being landlocked, it has greater amount of energy that is being given to the Mediterranean Sea. The temperature will rise. While on the similar latitude you see in the Atlantic Ocean, the temperature is relatively much colder. Why? It is landlocked. Then comes submarine barriers. It is quite possible. Let us say if you go to the deep oceans, you will realize that there are certain regions where, let us see, like this is the coastal region. Let us say a region where a barrier might be there, and like this. Like this is the open ocean, let us say. This is the barrier. What happens is, because the temperature, let us say this is all water, underwater. Because the barrier is present, there is a possibility that the temperature at this level might be, let us say, 5 degrees Celsius. But over, not 5, let us say 15 degrees Celsius. Over here, it might be 2 degrees Celsius. Why? Because it is basically being surrounded by this barrier. So what happens is that temperature might not be exchanged too much with the outward or the open sea. So the heat that is gained is little bit preserved also, and further it is gaining heat from both the sides. So the temperature might be higher of this particular region. So this is again submarine barriers that influence the temperature of certain parts of the oceans. So these are again the various factors that are present. Hopefully it is understandable to you. Now let's come to this particular topic, very important. Vertical temperature distribution. Vertical means as you go deep inside the ocean, how is the temperature basically varying? Let us understand this very, very clearly. Let's see. When I talk about the temperature variation, I'll be explaining this in detail in the future slides, so don't need to worry about that. I'm just showing you here what this diagram is representing. This is basically representing the temperature changes. How? The temperature is 0 degree till here it is increasing till 24 degrees. Till 24 degrees. This is the depth which is increasing, right? From 0 meters till the depth of 4,500 meters I've shown. Now I've shown you 3 layers over here. Important ones being, see, the important thing you need to remember is this is layer 1. This is layer 2. And this is layer 3. This is the surface layer. This is a layer which is known as thermocline, where the temperature decreases very rapidly, and this is the deep sea layer, bottom layer. This line is basically representing the fall in temperature as you move down. At the surface layer, let us say 22 degrees Celsius over here. Further, the change is not very high, but as you enter this layer, there is a rapid fall in the temperature. And further, if you move, there is no rapid change. So in the deeper layer, the water density is, as it is very high, the temperature is already decreased. So you realize that the temperature is not varying to a great extent, but this is the layer where the temperature is going to change. This is what we're going to study now. Now see, what we are studying here is the first layer. This is the first layer. First layer of the upper layer. Now please see, why we have to need to study this very carefully. There's questions are repeatedly asked from this particular chapter. You'll see, understand why. This particular part which I've written, many times questions are asked. Let's see. I have made this diagram. The surface layer has a temperature of 22 or approximately that. The average surface temperature itself is 27 degrees Celsius, we know that. But I've taken just a representation here. This, let us say, represents 22 degrees Celsius at the surface. Now, temperature representing 22 degrees Celsius at the surface basically means that this region is not referring to the polar region. Why? Because of the polar region also you have a temperature which is very cold here. So, in the polar regions, you will not see a very appreciable change in the temperature as you move down, because as it is, the temperature over there is cold. That is why in the tropical regions, this layer is present throughout the year. While in the mid latitudes, this layer develops only during the summer season, because in the winter season, the temperature is already low. So what will happen? You will not see any appreciable change. That is why this layer will only form in the mid latitudes or the high latitudes during the summer months. But equatorial region, as it is, there is high temperature throughout the year, so you will see the temperature being high throughout the year. So there is no problem in that. So that is why you see this diagram which I'm representing is present in the equatorial region or the tropical region throughout the year, but in the mid latitude only during the summer months, because in the winter months you will not see this rapid fall, because already the temperature of the surface layer is also going to be high. Clear? First of all, let's come here. The top layer represents the warm oceanic water and is about 500 meters thick, with a temperature ranging between 20 degrees Celsius and 25 degrees Celsius. So 20 to 25 degrees Celsius is the temperature that is ranging, right? Now, this is, I've already explained you that this layer, upper layer, is formed in the equatorial region throughout the year, but in the mid latitudes during the summer time. Second layer, this is the upper layer. Second layer is the thermocline. Now, this is a second layer called the thermocline layer that lies below the top layer or the surface layer. This is known as a transitional layer. Why it is known as a transitional layer? Because this is a region where the temperature rapidly falls as you move down. It is basically present from 500 meters depth to 1000 meter depth, and characterized by the rapid fall in temperature. So you see over here, let us say if it is close to 20 degrees, over here by the time you come it is close to 5 degrees or even more. Rapid fall. That is why this thermocline layer is very interesting layer, that is rapid temperature fall. Last is a lower layer. Now this is a third layer or the lower layers, and it is very cold over here. Represents the dense ocean water mass. So over here you realize that already the water is cold, dense. So there is no appreciable fall in the temperature. About 90% of the total volume of the water is found in this particular region. So you should be aware of this. This is the third or the lower layer where you have 90% of the volume of water. Temperature variation with depth in this zone is relatively very less or negligible, right? Okay, let's move ahead. Now comes to, we have done with the horizontal distribution. Let us see the vertical distribution of water. If you see the horizontal distribution, what does horizontal mean? That horizontal basically means that you are basically, if I see a map, what are the changes that are taking place? What are the variations that are present there? This is what is to be understood over here. Clear? So please write the heading horizontal distribution. Please write it down. So students, we have basically covered the vertical distribution of temperature, right? Now let us move on to the horizontal distribution. Let's see. When we talk about the horizontal distribution, what does it mean? Vertical distribution basically refers as you move deep inside the ocean or a sea. What are the variations in the temperature which we had seen through the upper layer, the thermocline, and the deep layer, the third layer. When we talk about the horizontal distribution, we see that when I see the map for that matter, let us assume these. What is how the temperature is varying in the oceans, right? Let's see. The average surface temperature of the ocean is about 27 degrees Celsius. Now this is something very important, because these are small things which are very often asked in the examination also, which we tend to neglect. Now we know that very well, as we have seen in the factors also, as we move in the latitudes, one after the another, in the higher latitudes the temperature is relatively very low, and the decrease has already been seen. Please remember, do not get confused with the concept of normal lapse rate and all, which we have done with respect to the atmosphere. This is with respect to the oceans which we are doing. Clear? So average temperature gradually decreases from the equator towards the poles, and it is approximately, see, it is on an average we have taken approximately 0.5 degrees Celsius per latitude. Now, if you are 20-degree latitude, the temperature average, please remember, it will vary according to the landforms and a lot of other circumstances and situations. But on an average, 20-degree latitude has 22 degrees Celsius. 40-degree latitude has 14 degree. 90-degree poles less than 0 degrees Celsius or close to 0 degrees Celsius. It is obviously less than that. So we see that the temperature is decreasing of the oceans which you move in the high latitudes, right? This is again important. Next to the northern hemisphere oceans record higher temperature. Why? I've already told you that the northern hemisphere has more land mass or more continent present. So the continents again heat up quickly. They tend to give their heat and energy to the oceans also. So they help contribute or help in the heating of the oceans also. So that is why you realize that the oceans in the northern hemisphere are relatively more warmer than the southern hemisphere. Next. Decrease in temperature with latitude in the Atlantic Ocean is less. Now these are certain statements which can be asked in your prelims as well as mains. Decrease in the temperature within the latitude in the Atlantic Ocean is less. See, over here, the temperature which is, the rate at which the temperature is decreasing is very less. You see 0 degrees Celsius over here, though conventionally if you see, these are very cold regions, but the temperature should be much below 0. The reason behind it is the current, ocean current. We will do the ocean currents in this lecture, but let me give you a brief idea. See, over here, there's a current known as the Gulf Stream. Gulf Stream. This is further continued in the form of North Atlantic Drift, which we'll see later on, don't worry. This is taking the warm water towards the northern parts of the Atlantic Ocean. And that is why you realize that the warm water is spread or spilled over here. That is why you realize that the decrease in temperature is not very rapid because the warm water from the lower latitudes have gone to the upper latitudes. Secondly, this also is very advantageous. Why? Because these regions, which you see the Scandinavian countries and all, these regions even during the winter months have very often ice-free coastal regions. Why? Because the warm current that is being brought from the lower latitudes by the Gulf Stream as well as the North Atlantic Drift helps them to keep the coastal regions ice-free or non-frozen. This is very useful. That is why over here you see the statement is mentioned, decrease in temperature with latitude in Atlantic Ocean is less, right? Next is enclosed seas like Mediterranean Sea show higher temperature than the Atlantic Ocean. There's a very simple reason behind it. This is Mediterranean Sea, this is the region. You will see the Mediterranean Sea will show a very higher temperature in comparison to the Atlantic Ocean, which is just neighboring it. Why? Because Mediterranean Sea is surrounded by land. So the amount of heat that is garnered or gained by the land is also given to the these Mediterranean Sea. And that is why it raises the temperature also. Clear? Okay. So when we see this map, you can roughly get an idea that this is the temperature variation which you have seen. This is because of the ocean currents. Over here also if you come, this because 25 degree isotherm over here is basically going down because of the south equatorial current. Similarly, you realize that Oyashio current over here, Kuroshio current over here, all these currents are also influencing the temperature that is present. We will be seeing the currents, then we will be better able to analyze it also. Meanwhile, you can just keep in mind few things, that is the Mediterranean Sea, the Atlantic Ocean thing. This is something that is very often asked. Okay. Now, heat balance of the ocean. You have already done the concept of heat balance of the atmosphere. Now, that is something that is present in the NCERT. But this part is not present in the NCERT. And this is something that can be asked. So heat balance of the ocean, like the atmosphere, similarly there's a concept of heat balance of the ocean also. So let us see few concepts. You do not have to go into R&D, you can just listen to it. This is important. Addition of heat to ocean and heat lost. How the heat can be added to ocean, how it can be lost. Let us say heat can be gained through insolation, HI. Heat can be gained through, let us say, floor or continent from volcanism, through sensible heat, through kinetic energy due to the compression of the seawater, salt water, which has salt. So these are the ways through which heat can be added to the ocean, and there are mechanisms through which it can be lost, through evaporation, through convection, and through radiation. Now, having known these processes or factors through which heat can be added and through which it can be removed, let us see this. Heat added is equal to heat lost if it is proved. That means it will help us to understand that heat what is gained is being lost. So there's a balance maintained. So through insolation 90 units, through ocean floor 9, kinetic energy 0.9, sensibility 0.01. So there's 100 units that is gained. What is lost? See, through radiation 41 units, through evaporation 54 units, through convection 5 units. So total 100 units again lost. So there is a balance that is maintained with respect to what is gained and what is lost. Clear everybody? So understand that well. Now let's move ahead. Let's come to the topic of salinity of the ocean. Now please understand one thing before we move ahead. Very often you have studied, before I tell you this, when I talk about 7 and like this is 7%. What does this mean? 7 per 100 parts. Can I say this? When I say 7%, can I say 7 per 100 parts? Or can I say 7 upon 100? Can I say 7 per 100 parts? You can say this. There is nothing wrong in that. Similarly, please remember, if you take that analogy, if I write this statement, 7, 2 dots, it is not now per 100, it is per 1000. It is now 7 per 1000 parts. Always remember this. When one dot and one dot over here, this means 100. If there are 2 dots here, this is out of 1000. If there are 3 dots, then that means out of 10,000. Clear? Now understand this. When we are going to talk about salinity, everywhere, even if I have not written this symbol, keep it in mind, it is per 1000 parts. Remember that. Because there is a map that I have drawn here. Where is it? Just let me show you. Over here, and I have just mentioned 35, 36, 37. So it is all of them are in per 1000. Clear? Okay. So what is salinity? Salinity is the weight of the dissolved material upon the weight of the sample of seawater into 1000. So based on that, we get to know about what a salinity is. The estimated salinity or average salinity of the ocean is basically 35 parts per 1000. Now when I talk about the ocean, please remember it is not only the sodium chloride or the table salt which we talk about. There are other salts also that is present in the ocean or the sea water. Now this can be asked in your paper also, and then there they can ask you to arrange them in order, because this has been asked in the CAPF paper also by UPSC. So it can be asked in civil services also. NaCl 77.8%, MgCl magnesium chloride 10.9, magnesium sulfate 4.7, CSO4 calcium sulfate 3.6%, potassium sulfate 2.5, calcium carbonate 0.3, magnesium bromide 0.2%. So this is an idea approximately of the salts that are present in the ocean. So it is not simply sodium chloride. There are a lot of other salts present. Their order can also be asked. So please be careful in your mind, particularly in the PCS, particularly in the CAPF paper, particularly such types of paper. These are very frequently asked, and in the UPSC paper also they can very well ask you. Clear? Okay. What are the factors impacting salinity? Let's see. First is evaporation. See, greater the evaporation, please understand why the ratio is, the question is weight of dissolved material, that is a salt that is present, upon the weight of sample of seawater. Now, if the evaporation is taking place, the weight of the sample of the water content will decrease. Obviously, the salinity content will increase. So, more is the evaporation, the salinity in that particular water will increase. That is why if you realize the Mediterranean Sea, in Mediterranean Sea, the salinity content is relatively very high. Why is it high? Because over there, the evaporation is taking place at a very rapid rate. Landlocked region and evaporation is high. So, salinity content is very high over there. Next comes precipitation. Now, when the more water is added, it is like, for example, if there is a glass of water, you have certain amount of salt that is added to it. You add more water, you will dilute it. Earlier, when you had added salt, you were not able to drink because it was the parts per 1000. If you realize it from that perspective, it was very high. But after that, when you have diluted it, it is not drinkable because the dilution of the salt has taken place, or the amount of parts per water have increased. The water content has increased. So, when I talk about the precipitation, more water is being added to the water body, so the salinity will decrease. Similarly, this example is Baltic Sea. When the precipitation takes place, the salinity is very low. Third is influx of rivers. Those regions where rivers or freshwater is being added through the rivers, In those regions, the salinity of those particular parts are going to be relatively lower. If you compare it, that is why if the Bay of Bengal region where water is being added to it by Ganga river, Brahmaputra river, so you will realize the salinity content is relatively lesser. If you talk about the ocean currents, you should understand this very well, that ocean currents are also very, very important perspectives with respect to the salinity. Now what happens sometimes is that the ocean currents are those drivers which take or vary the salinity. Supposingly in a region a ocean current is going, it might carry certain water from a region to another region. Or let us say when there is upwelling, you will realize that there is a possibility, we've already done upwelling where cold, dense, saline water can come up. So that region where the upwelling is taking place, there's a possibility that more salinity can be present there. So with respect to upwelling and downwelling also, you can realize that ocean currents also very significantly impact the salinity of a region. Next, ocean atmospheric circulation. Now please understand, when I talk about atmospheric circulation, let us take an example. Example is high pressure. When I talk about high pressure, let us talk about if a high pressure center is located, can I call it anticyclone? If the atmospheric circulation we're talking about is anticyclone, it is going to prevent the rainfall taking place predominantly. Obviously, there are a lot of other phenomena that are taking place. But if there is a high pressure region with an anticyclonic condition, then it is going to bring aridity there and it is going to prevent rainfall from taking place. So, if there is high pressure region and atmospheric circulation with respect to high pressure region or anticyclone, you will realize there is going to be prevention of rainfall taking place there and more aridity. And that means that there is going to be an increase in the salinity over there because it is going to be more arid. Rather than precipitation, there might be more evaporation taking place. So, the salinity will increase. Next is anthropogenic activities. Now, these are very discrete or very like broad category where it depends upon what type of activities human beings are indulging in. Supposingly, they are indulging in, let us say, some factories or some, let us say, some mineral factories are there, more mining is taking place in certain regions. Now, that might add salt to the coastal region. So, those all factors, wherever human beings are involved, their responsibility with respect to certain addition of salt will or deletion of salt will be referred to under the category of anthropogenic activities. Clear? So, these are all factors which are basically responsible for the salinity. Vertical distribution of salinity, please remember something very similar to what we had done in the temperature. There is another similar category over here. Please see. When I talk about the region where these are two types of lines I have drawn, one in the lower latitude and another in the high latitude. Please remember, let us take the surface. This is the surface layer. There are three layers again here. The surface layer, then you have the halocline. Halocline is very similar to the thermocline, but over there thermocline the temperature was decreasing rapidly or changing rapidly. Over here the salinity is varying very rapidly. So this is not a halocline layer and this is a deep layer, third layer. Now see, first of all, let us see the surface layer. Do you realize in the lower latitude the salinity is 37 parts per thousand, while in the upper latitudes it is 33 parts per thousand? Something very interesting to hear, that the salinity of the regions which are close to the equatorial region has higher salinity in comparison to those which are in the higher latitudes. Anybody has thought about it? This is something very confusing for some people. How is it possible, sir? Because many people say that there is a lot of rainfall in the equatorial region, so how come? Please remember one thing very clearly. Firstly, when we talk about the equatorial region, we need to understand if there is a lot of rainfall, there is a lot of evaporation also taking place. So the evaporation that is taking place is of a great extent. Now, evaporation is a force that is basically trying to increase the salinity and precipitation is trying to decrease it. So overall, the balancing effect ends in close to 37. That is again the average salinity also. But when I talk about the coastal region, you know that it is a region where high pressure is located and you know the rainfall is not there. Now in those particular regions, we should understand that it has fresh water. Those glaciers and the snow are stores of fresh water. the melting of those glaciers add fresh water to the regions of the colder or the high latitudes. And that means like over here, there were two contradictory forces acting. One is pushing the salinity higher, other is decreasing. But you realize overall balancing effect brings the salinity to an average value of 37 parts per thousand. But in case of the higher latitudes, you see that the melt, because there is no evaporation as such a great extent taking place, because there is, as it is, very cold conditions present. Yes, there is evaporation in every temperature, but the extent is kinetic energy is less with respect to the water molecules because it is already frozen most of the cases. So over here, the melting of ice is adding a lot of fresh water. Now the melting of ice adding fresh water decreases the salinity of this region. Yes. Now the important dimension over here comes. That is why at the surface layer, the water over here at the surface level, the colder region has less salinity. As you move down, this factor of fresh water being added over here is a predominant factor that decreases the salinity at the surface level. But as you move down, you realize there will be similarity over here. Over here, it is high because of the evaporation and all. As you move down, halocline, both the things will, again, this will decrease and this will increase, because both the factors in the surface level are not present over here. So slowly they will almost become close to each other. So this is the layer of lowest density also. Now please understand, it has thickness of 100 to 200 fathoms, carries 2% of the total volume of the water. Density is liable to obviously temporal variation, but what is important here is that the surface layer, at the surface layer, two things are important. First, the lower latitudes have a different salinity in comparison to the higher latitudes. How? Let us see. The lower latitudes have higher salinity. Why? Because of the arid conditions. Arid condition, the way, due to evaporation, not arid condition, just please write it again. Evaporation, not arid condition, evaporation, very high. Not arid, evaporation. Evaporation being very high, so that means greater evaporation. On the other hand, you realize that there is rainfall also, so the balancing effect comes to be close to 37 parts per thousand. But over here, when you see, there is low salinity. This low salinity is an outcome of the fresh water that is added by the glacial melting add water. Now this is already fresh water. So this decreases the salinity at the surface level. So these two things are again the most critical over here. Clear? Now if you come to the next layer, that is halocline. The halocline is a layer just below the surface layer where there is rapid change in the salinity. At the ones with the lower latitude over here, you will realize that it is going to decrease, while on the higher latitude it is going to a little bit increase, so that they come close to each other. Halocline separates the surface layer from the deep layer. Then you have the deep ocean. This is more or less uniform with respect to the salinity due to the accumulative effect of denser, saltier water from the evaporation and sinking processes limited freshwater input. So these are the basic aspects. In the deep layer, as we had seen with respect to temperature also, you realize that it is almost the similar site of salinity is present. Clear? Okay. Horizontal distribution of salinity. Again, as we had done with respect to temperature, we are doing this also. The average salinity is around 35 parts per thousand. The highest salinity is between 20 to 40 degrees, which is 36 parts per thousand. Now, the important thing is over here, why is the salinity highest around this, not at the equator? You know that the equator, again, please remember, again, evaporation is more, precipitation is also there. But if you see over here in the case of the region little bit above north of the equator, over there you realize the precipitation is also there, but precipitation is little less, but evaporation is very high. So in those regions, you realize the salinity is again tremendously high because high temperature, high evaporation and low rain. Average salinity around 10 to 30 degrees south, that is 35 parts per thousand. From 40 to 60 degree north and south, again 31 to 35 parts per thousand. Salinity decreases around the polar regions because of the influx of melting ice. Overall, the northern hemisphere have 34 parts per thousand and southern hemisphere have 35 parts per thousand. Now, the important dimension is more fresh water added and less evaporation. That is why you realize that the salinity is 34 parts per thousand here. Write it down. Write it down here. Why? Please understand, na? Why southern hemisphere have more salinity? The northern hemisphere has higher temperature of the ocean, but the southern hemisphere has more salinity. Why? Southern hemisphere, you do not have land, so the evaporation can take place more because of more water surface is exposed. In the northern hemisphere, you have the continents also, the lesser ocean surface is exposed to what? To evaporation. Because you know that the surface area is directly proportional to the evaporation taking place, so lesser the surface area being exposed, lesser is the possibility of evaporation taking place. In the southern hemisphere, you have more area of water because it is more of a water body, because in the northern hemisphere, you have more continents. In the southern hemisphere, you have lesser continents, more water. So in that case, more water is exposed to evaporation taking place. So that is why the salinity is little more in comparison to this, because in northern hemisphere, because the land is also there, so water through the rivers can also be added. So that is also a fact. So fresh water addition and less evaporation. So these are the two major reasons. Clear? Okay. This is again roughly, let's see here. Again, over here 35, but as you move ahead, 37 over here because of the evaporation being more. The salinity has gone. See, this is again, the salinity is 35 over here because the North Atlantic drift is taking the salinity upward. Similarly, you realize these are the salinity distribution based on the like 35 over here, 30 here, 32 here. 32 here, why? Because Antarctica melting ice is there, so it will decrease. In these regions, obviously, where there is 37 here, 37 here, because these are the regions of high evaporation and lesser rainfall. That is why it decreases. Otherwise, this is how the distribution is. Little bit above the and below the equator, you have the higher salinity. As you move upward, it will decrease. As you move downward, also it will decrease. Next comes a very, very important topic, that is the motion of the oceans. Let us study them one by one. Okay. Movement of the oceans is basically again a very important factor which we're going to study with respect to the tides, ocean currents and waves. When we studied this chapter, there are two types of motion which are broadly described in the NCERT. First is the vertical motion, which is the tides. Horizontal motion includes the ocean currents and the waves. Now you need to understand why this is so. Please see. If you see here, let us understand the reason. If I see the tides, now tides are basically rise and fall of the water because of the gravitational force of the sun and the moon. And that is why it is just rise of the water level. So that is why it is known as what? A vertical motion. So it is type of motion is vertical. Now let us see the ocean currents for the timing. Now ocean currents are like rivers in the ocean, which are basically following the direction of the prevailing winds or the winds. So they are moving from one region to another. So it is like a horizontal movement, that is sideways along the surface. That is why it is a horizontal movement. Now comes the ocean waves. Please understand, ocean wave is not the movement of the water. Waves are created because of certain disturbing force that is created or acted upon the water. Whenever you add certain, let us say there's a water surface, you add a finger there. There will be ripples created on all directions. A very miniature waves. Why? It is not that the water is moving. It is the energy that you have supplied to the water is basically being transferred. That is also being transferred in what? The horizontal manner. That is why that ocean waves are the energy moving sideways or in all direction in a horizontal manner. So these are categorized into horizontal motions and tides into vertical motion. Let us begin first tides. Now tide again is very interesting concept. We will be studying various dimensions associated with it. So please understand it. When I talk about tides, tide is what? A periodic rise and fall of the sea level. What it is? It is basically a periodic rise and fall of the sea level. Now, why it is being caused? It is basically being caused by the attractive or the gravitational force of what? The moon and the sun, right? Now, you will say that sun is so far away and still it is exerting a force, and moon also. Yes, see, we need to understand that overall impact with respect to the tides, it is more of the moon than of the sun. The reason is we know that sun is tremendously huge, but it is very far off, while the moon is close by. So again, the gravitation is also dependent upon the distance between two bodies, right? So when the distance is less, the force that is being exerted on other body is also more. That is why, though sun is also contributing to the gravitational force, the moon is also contributing, but the impact that the moon causes is relatively more because it is just a neighbor of the earth, right? That is the reason. Now, attraction by the sun and the moon. Now the characteristics. First, periodicity. Tides occur at regular intervals. Unequal height. The successive tides might not be of the equal height because again it is depending upon the gravitational pull, and that is dependent upon the position of the moon. Influence the coast. Now the tides that are coming also influence the coastline also. They might shape the coastline. Predictability. Because we know the movement, the speed of the moon, we know the speed of the rotation of the earth, the revolution of the moon, and all these factors are known. So astronomical calculations, you can basically predict very accurately where the tides are going to happen. Next is vertical motion. It involves rise and fall, which we've already studied. Next is ecological and economic importance. They're of great importance, particularly like navigation. Shallow ports, tidal energy or mangrove ecosystem protection are also one of the important means which are being met by tides. So these are what the characteristics that you all should be very well aware of. Clear? Okay. Let's move ahead. Let us understand, leave this diagram for 2 minutes. Let me hide it rather, right? Let us see this diagram does not even exist, okay? Let's come here. When I say what are the causes for the tides, something very, very interesting. So what causes tides? Please make us understand this. See, I've already told you something that it is caused by the gravitational force of the moon and the sun. When I mention these, this is not so easy that it appears to be when I tell you, right? It is very easy to sound or very soothing to sound that it is due to the gravitational force. Now, there are a lot of complex issues, types that are basically being dealt over here. We'll deal with them in the coming slides also. First, let us take only the moon. This is Earth, this is moon, and this line that I've drawn, it is basically representing that the water is being pulled by the gravitational pull. Water from the Earth is being pulled, and that is why the tides will come. So this is known as a tidal bulge, right? Gravitational pull basically leads to water being exerted, force being exerted, and that is why water in this side, which is facing the moon, will be pulled towards its side, right? Pulled towards its side. So this is known as a tidal bulge. Second things, for the timing, let us say for 2 minutes, let us forget this moon also. The sun's gravitational pull. Now, sun's gravitational pull is also being exerted on the earth. Now, it will also pull the water, whatever gravitational forces has. So, this will also create a tidal bulge. Now, these are two phenomena that, okay, it's fine, understood. Now, it will depend upon what is the position of the moon and the sun also to actually get what the tidal bulge or the strength of the tide is. That will depend upon that, which we'll be seeing in the next slide. Now, there's one other very interesting concept that happens. Supposingly, the tidal bulge is being created. Now, water is being pulled this side, right? Now, you know that there is a basic concept that Earth has to maintain a balance with respect to the forces that are being exerted. Now, when the force is being exerted inward in this direction, there will be a counter force that will be generated in the opposite direction to balance the gravitational force. This force is known as the centrifugal force, right? So this is what? This is because of the gravitational force. This is because of the gravitational force of the sun. Now, there is another force that is created, which is on the opposite direction. Which is known as the centrifugal force. Obviously, there is going to be a tide bulge over here also, but this is in opposite direction of the gravitational force. Why? Because in order to balance the gravitational pull of the moon or the sun, a tidal bulge is created on the exactly opposite side so that it balances that force, and this is known as the centrifugal force. The centrifugal force. Now, if I combine all these three diagrams, let us see the result. Sun and moon are exerting gravitational force. So this is a tidal force. This is a tidal bulge that is created. Let's write it down. This is a tidal bulge. This tidal bulge is due to the gravitational force, right? It is due to the gravitational pull. Gravitational pull of, let us say, of moon and sun. Moon and sun. Let us write it this way. Now, on the other hand, you know that this is also a tidal bulge because this is moving out. But this is not due to the gravitational force. This is not due to the gravitational force. The reason behind it is that it is because of the force which is countering the gravitational force. That is how stability is maintained. So the force is being exerted here. It is a counter force being exerted here. That is because of the centrifugal force acting in the opposite direction. Opposite direction. And that is why the resultant is this. So you have at any particular point, if you are having a high tide in one place, you will be having a high tide exactly at the opposite place also. So if two places where there is low tide, you'll be having low tides in the opposite direction. Opposite. Like if there's earth over here, if there is high tide here, there is going to be high tide here. There's low tide here, there's going to be low tide here. Clear? So this is the reason. So this is the cause overall if you study. Now let us study the type of tides, right? Now we had studied that, okay, gravitational pull is there, all those stuff. That is very interesting to study and understand. But the important thing more over there is that what is the position of the moon and the sun? Now see, let us study the type of tides on the basis of the position of the sun, moon and earth. Let's see. There's one concept known as spring tides. What are spring tides? Whenever the sun, moon and the earth are in a straight line, whenever they are in a straight line, in that particular case, let us remove this for a timing. When they are in a straight line, the gravitational force which is basically attracting the water is again combined. That means the gravitational pull is combined of both the bodies. So what happens is the tidal bulge that is created again the gravitational force will be more, because this is gravitational pull of moon plus gravitational pull of sun combined because they're in the same direction. And we know that very well, there will be again a high tide over here also on the opposite direction. Now see, this is in the case of when moon is between sun and earth. In this case also it can happen. On the other hand, if the condition is of a full moon, then also it will be adding. Why? Because water is being pulled here by moon and water is being pulled by in case of the new full moon condition by sun. So in both the cases, then also the tide is going to be much more than the average tide. And that is why this is known as a spring tide, much more than the average tide, right? That means it is very strong also. Now, if I've said that both of them are in one line, so it can happen twice a month, one on the day of new moon, another on the day of the full moon. So when the sun, moon and the earth form a straight line, the result is in a higher tide level above the standard or the normal tide. That means more than the standard or normal tide. Clear? So this is again being represented in the form of spring tide. Now there's something else that can happen if they are not in a straight line. Now let us see this. Supposingly Now the moon can be here also. Anyway, we are taking this example. Now the sun is going to exert some gravitational pull. So it will try to have a tide in this direction. So water over here, you will have no tide, lower tide. Over here it is high tide. But on the other hand, the moon is also present in that way. So it will try to pull water that side. So you will have a tide which is much lower than the standard tide because the gravitational pull is basically being subtracting. So you will not have normal tide also. You will have much lower than the lower normal tide. So this is known as a neap tide. What is neap tide? When the sun and the moon and the earth are at right angle, the resultant tide is lower than the average tide. Why? Because the gravitational pull overall, the net gravitational force is again getting subtracted. Can I say gravitational pull of moon minus gravitational pull of sun? Because the gravitational pull of the moon is going to be more over here with respect to tide because it is closer. That is why. Net gravitational force is gravitational moon minus gravitational force by sun. So it is going to be less. In that case, it was being added. It is being subtracted here. So obviously, it will be much below the normal tide. So it is called a neap tide. Clear? Okay. Next is magnitude of tide based on the aphelion and perihelion. For the timing, let us take one by one. Let us leave this part. Let's see here. This is Earth, this is Moon, this is Sun. Now, if you see, perihelion is a condition when the Earth is nearest to the Sun. When it is nearest to the Sun, you will realize that it will have tides which are relatively higher or a greater degree. Why? Because the distance is less, so the gravitational force being exerted will be much more than when it is far away. So what happens here? Can we write it here? Here at perihelion, perihelion means nearest to the sun, right? It is close to on 3rd January. Over here, sun will exert more gravitational force on Earth, thus a higher tide strength. You can call that also. On the other hand, and this generally takes place around January 3rd, when it is closest. At aphelion, if you realize, at aphelion, the reverse will happen. Reverse will happen. Reverse in the sense that the tide is not going to be strong because the distance is more. The distance is more. So strength of tide lesser than usual. Lesser than usual. Clear? Same thing exactly comes when we talk about perigee and apogee. Perigee and apogee is basically with respect to the distance between the sun, between the moon and the earth. Perigee is a position where moon is closest to the earth. So what will happen at perigee? At perigee, you know the force of the gravitational force being exerted by the moon on the earth is going to go very high. Moon will exert high gravitational force on earth. Thus this will lead to higher than usual tides. At apogee, you will realize distance is more. So the gravitational pull will be less. Gravitational force is less. by the moon that is exerted on the earth to pull the water, right? That is less. So the tide, the strength of the tide is going to be less. Tide less or less than usual or standard, as we say. Clear? Okay. Now, on the basis of frequency also, there are certain books which classify them on the basis of frequency. That means how frequent they happen. So there are semi-diurnal tides. The most common tidal pattern featuring, that means there are two high tides and two low tides in a day. This is semi-diurnal. Then there are diurnal tides. That means there is one high tide and one low tide in one day. And mixed tide, that there is variation with respect to the height of a tide. So this is known as a mixed tide. So these are again a third categorization of tides which we study here. Next comes, with respect to tide, there is a very, very important concept which is very often neglected but very important, that is mentioned in one line in the NCERT. So like Ford's concept was asked in the NCERT in the syllabus this time in the UPSC paper, so this can also be asked. Tidal bore. Now what is tidal bore? Please see. Tidal bore are basically very remarkable phenomena that manifest when tides surge into the narrow shallow river estuary. Let us assume this is a land and there is a river that is flowing in this direction. There is a river that is flowing in this direction. Now, when the tides basically come from this direction, what happens is the rate of flow of the river is already very less. Why? Because it is at the lower stage. It is not at the young stage where the water speed is going to be very high. It is not that case. Where the water is going to be flowing very gently because it is merging with some sea or ocean. Now at this moment, when the tide basically comes at a very fast pace, it will create certain wave-like structures which is known as tidal waves, and the water will start moving in the reverse direction. So the water will be moving in this direction. These are tidal waves which are known as tidal bore. People sometimes even use them for surfing also, right? In Chinese region, in China also. So this leads to tidal waves whose leading edge are nearly vertical. That means the waves type structure that are created, they are almost vertical. It depends upon the strength also. Now every region does not have such strong tidal bores, but in certain regions, yes. Like the Quanting River in China, they experience relatively very, very strong tidal bores. So this is again a very important concept that you should know. This can be asked in 10 markers. Significance of the tides, they are used in navigation, like the Haldia Port in Kolkata you have seen. Fishing, high tides attract fish closer to the shore, so they can be useful for fishing activities. Next, you have the desilting. When the tides come, they remove the silt or the sediments that have been deposited by the rivers along the coastal region. Coastal erosion management, they influence the sediment supply that has come. So that means they're managing, because what extra sediments are there, they can be removed, and whatever certain new sediments are required, they can be brought by the tides also. Tourism and recreation, like surfing activities can be there. So they're a hub of tourism activities also. Ecological significance, tides bring nutrients. Now these regions are very useful because there is a mangrove ecology might be associated with this. There are coastal ecosystem that is there. So the nutrients might be brought to these regions which are useful in balancing the ecosystem. Climate regulations, again, these are again helping in climate because they sustain the mangrove system also, coastal ecology. So they can be very useful for maintaining the or regulating the climatic conditions also. Particularly the coastal regions. Energy generation, now these can be used for generating energy. For example, 3 megawatt at Durgadurai regions in West Bengal has been basically implemented over here. So it can be used for generation of electricity also. Let's move ahead. Waves. Now waves are again something very, very common, but again we should understand these. There is no movement of water. It is simply the movement of disturbance. Waves are oscillatory motions. I will tell you why oscillatory. You will understand that also. When I go ahead, I will be explaining you. Like for example, there's a wave here. The motion is like this, right? Beneath the ocean, right? These are round oscillatory motion that are going on. Clear? Oscillatory motion of the water where rising and falling takes place. Why rising and falling? Again, this is the crest, this is the ebb. This is how the waves move. Rise and fall, rise and fall. The disturbance are traveling. So this is what again is rise and fall, leading to circular motion of the each wave particle. So over here, this is a circular motion of the oscillatory motion that is taking place of the particles. Now, they are moving energy. See, they are moving energy. Why I'm saying moving energy? Because the disturbing force that has been created, that can be due to earthquake, that can be due to wind, that can be due to volcanic eruption. They can be created because of any of the factors. Like tsunami is also waves, great harbor waves. Why? Due to, let us say, volcanic eruption or earthquake, underwater earthquakes. In that particular case, you will realize that these waves can be very huge. Now, these waves are not water traveling. These are basically disturbances that are traveled because of the shock wave that are created. So, these are moving energy because the energy is being supplied to water, and that energy is being basically moving, or the disturbing force that is moving. Now, characteristics, these are oscillatory in nature. We have seen there are horizontal transmission that is moving from, the disturbance is moving from one place to another. Generating force are generally the wave, the wind also over here. Wind can be one of the factors. Various others. Generating force is basically, again, short lifespan. When the waves move, after some time they clash with the coast, or they do not have a very long time span, unlike the ocean currents. Transforming the coast, because when they clash with the coast, they might even cause erosions also. So they might change the shape of the coastlines. They have varying height. Again, the height will depend upon the extent to which the disturbing force has been acted on the water. Causes of waves. First is air-water interface. Now, wind blows across the ocean surface. Wind can itself blowing create waves depending upon the speed of the waves. Water surface. See, when the water of different densities basically come together, there are like different water masses. Why? Because they have different density. When they come together, it is like two bodies coming together and hitting. And then on other direction, the waves can be created. So water-water interface, it can happen. Mass movement. Now see, it can also happen. Mass movement means, let us say, around the coastal region, there is large landslide or water, let us say, large boulders basically fall inside the water. Now that will lead to waves being created. Or let us say huge ice particles or large glacier, let us say mass of rock, mass of ice has broken and fallen into the ocean. That can also create waves, and those are known as splashing waves or splash waves. Why? Because something has fallen in the ocean and splash is being created, and that is leading to the creation of waves. So those are another splash waves. Next is underwater regions. Underwater regions can be an underwater earthquake, underwater volcanic eruption that has taken place, underwater avalanche that has taken place. That can basically cause underwater aspects. Next is gravitational forces. Now the gravitational pull of the earth and the moon can also call tidal waves. Tidal waves are also a form of waves, right? Because of the tide, some waves can be created. You've seen in the example of tidal bore also. So these are also the categories, types, right? Or the causes. Certain important aspects that you should know. First, you have already understood the oscillatory motion. So let us see first of all, let me highlight it a little bit. This is a wave that I have mentioned here, right? Up and down, up and down, up and down. This part, which is the top part of the wave, the highest point of the wave is known as a crest. The highest point of the wave is a crest. This is the lowest part of the wave, which is known as the trough. This is known as a trough. Now, the distance between the crest and the trough is known as the wave height. The distance between the top and the low is known as the wave height. Sometimes what will happen is there is especially this imaginary line that is created here, and this distance is known as the amplitude. And amplitude, that is why, is referred to as half of the wave height. Now, the distance between one crest and another crest, or one trough or another trough, is known as wavelength. So this horizontal distance between two successive crests or two successive trough is known as wavelength. Two important concepts which are also there: wave speed. The rate at which the wave moves through water is known as a wave speed. Wave frequency, the number of waves that are passing to a particular point in particular point in a unit time is known as the wave frequency. The number of waves passing through a given point during 1 second or a unit time is known as a wave frequency, right? So these are the important concepts that you should be aware of. Again, these have been done in school also. You do it in physics chapter also with respect to waves when we study. This is something you should be aware of, and this is again simply applied to the oceanography chapter. Now, having done waves, I'm giving you a little bit of case study of tsunami. We have already done this earlier also, but why I'm giving you so that you understand this is also an example of wave. When I talk about tsunami, you have seen that tsunami, su means harbor, wave means nami means wave. Now these are great harbor waves. That means these are very huge waves that are created, which rise like wall, and they are so huge and they cause massive destruction when they hit the coast. Now that is why, please understand, there are certain features which are associated with it. Fast speed, amplitude increases near the shore, series of waves triggered by, let us say, earthquake or volcanic eruptions majorly. Wavelength is long, unpredictable, a run-up or inundation that they might go inside large region inside the earth or in the coastal region also, and deep inside because of the force and the water that is there. Multiple causes, sudden onset. Now, in order to remember these fast worms, initial words of all of them have been mentioned here, so you can remember the characteristics by this mnemonic. Major causes, fault movement. We've already done plate tectonics. You would have seen that if there is certain fault movement, you will realize that that will create a lot of seismic waves that are created. Now, these seismic waves are basically what? Again, forces that are going to trigger, let us say, a lot of energy, and this might lead to creation of upward forces, and these waves travel along to the coastal region, and these are also known as tsunamis. One. Second can be plate tectonics. You know that very well. These are various plate boundaries that you have seen in the topic of geomorphology when I was doing. See, movement of plates themselves can cause waves. All of the three can cause. If there are two conservative plate boundaries moving, there is certain motion that can also trigger certain waves. If there is destructive, if there is constructive plate boundary, there is two plates are moving apart, that can also cause certain amount of waves. But when I talk about the aspect of the destructive plate boundary, where it is thrusting or subducting below another plate, this actually leads to a lot of very large scale tsunamis also, right? So the destructive plate boundaries are very often associated with very large earthquakes, along with it very large scale tsunamis also. So these are, again, all of the three can cause one or the other way, but this is the most important one, that is the destructive plate boundary. Now, the release of energy due to the plate movements lead to creation of large waves which are known as the tsunamis, which we already studied. Now, another reason can be landslides. If supposingly this is a mass of land large that has basically moved down. When it moves down, it pulls the water along with it. What along with it? See, it has gone down, the water level has gone down, and this has risen. Now, these are like the waves that are created, which can also be very huge and which can again go to the coast in the form of tsunamis. Next is volcanic activity. Now, when the volcanic eruption takes place, it basically causes very large shock waves. Now, these shock waves again lead to large waves in the form of tsunamis, right? Okay. Others can be certain blasts that are done by human beings, certain bombs attack have been done by human beings, or some meteoroids have hit the earth. Those can also cause, again, tsunamis, right? So these are few of the causes. The most important means are generally volcanic eruptions and the earthquake. Now, if you see this map which I've shown you on the board, this is basically the Pacific Ring of Fire. Now, the Pacific Ring of Fire is, again, we have studied in the topic of plate tectonics, which I told you that this is the most active, tectonically active region. Being more tectonically active, so it has the largest number of the earthquakes and the volcanoes, which you can find here. And that is why you will realize this, that these are the regions which are more subject to tsunami also, because it is more tectonically active. Clear? So, if you see recently, on 30th July 2025, 8.8 magnitude earthquake basically took place near the Kamchatka Peninsula, right? And then tsunami warnings were triggered, though again, much destruction did not take place. So you realize that the reports that were released basically talked about a shallow reverse faulting that took place, which was basically seen over here for the earthquake. What is the reverse faulting? We have done already in the chapter of geomorphology. This is the hanging wall. Instead, when the hanging wall goes down, it is faulting. When this hanging wall goes up, it is known as reverse faulting. This is a hanging wall. This is a fault plane. If initially it is in this position, right? Normal fault is when this block moves down. But if this block moves up along, then this is known as reverse faulting. Now, this reverse faulting has happened because of certain compressional forces. Very important, because of some compressional forces which led to this massive earthquake taking place. We have understood that this is a reverse faulting case, but what were the compressional forces that took place that led to this massive earthquake taking place? See the compressional forces. The report also says that that there was subduction of the Pacific plate under the Oshkosh plate, which was creating the compressional forces. And that led to the reverse faulting, which led to the massive earthquake. So this is the again report. This is the report mentioning the same thing which I have mentioned here. Okay, coming to the next topic, that is ocean currents. The ocean currents are like the rivers that are flowing in the oceans. These are basically following the direction of the winds. Like if you see the map also, the ocean currents which I'll show you, they are basically following the direction of the winds, right? See, the ocean currents refer to the continued mainly horizontal movement of the ocean water. They are like rivers in the ocean. And they play a very important role in transferring heat or energy maintenance, right? The warm currents basically make the warm water travel towards the upper latitudes, whereas the cold currents from the upper latitudes to the lower latitudes. So it is trying to balance or maintain it. You've already studied this, that I've told you previously also, that when I was studying you the other parts, I told you that there is a concept of upwelling and downwelling, right? And you know that the ocean currents are not only surface, there are deep water currents also. We have studied that also. So you should keep that in mind. Characteristics. There is horizontal movement. There is permanent and long lasting because they are following the same pattern or same path. There are definite direction and path. They can be warm and cold. There are seasonal variations. In the Indian Ocean, if you realize, with the reversal of the monsoon, you see that the ocean currents also change. Impact climate and weather. Obviously, wherever the cold currents are flowing, they result in arid conditions. They might lead to deserts also. Wherever the warm currents are flowing, they might lead to increase in temperature of that region. Ecological and economic significance, very similar to what we had studied in the tides also. So you can see those regions are important for breeding grounds, for fishing, let us say fish catching. These are regions which influence the climate of the region. So as they influence the climate, they influence the daily life of the people also. Next, factors influencing the ocean currents. Let us see this. Wind. The friction between the moving air and the water surface is crucial role. So this is the surface of the water. The wind is flowing. It exerts pressure on them, that is frictional forces, and it forces the water to move in its direction. So wind is the most important cause for the ocean currents. Second is Coriolis force. Coriolis force means, again, as we had studied in the climatological chapter, as the winds are being subjected to the shift in the direction because of the rotation of the earth, similarly the ocean currents are also subjected to a similar direction. Gravity, it pulls down the water down and creates gradient variation. Solar energy, it causes the water to expand and because it gets warm. Salinity, it makes the water dense, so it might sink. Along with that, you realize underground topography. Underground landforms deflect the ocean currents. Similarly, the coastal landforms, when the ocean currents encounter a land, it tends to divert the direction because of the coast, and they start moving along the coast. So this is again deflecting the ocean currents. Let's move ahead. When I talk about the types, please understand we've already done something related to this, where I've told you that there can be cold currents. That means the cold currents are the ones which are taking the cold water from the upper latitude to the lower latitudes, and warm currents are the ones which are bringing warm water in the cold regions. On the other hand, if I talk about the depth, the surface water currents which are up to a depth of close to 400 meters, whereas the deep water currents are the ones which are flowing deep close to the sea bottom. And I have already explained you the concept of upwelling and downwelling in that case, right? What are the impact? See here, impact are first heat balance. Heat balance by the warm water taking warm water in the upper latitudes and the cold current bringing the cold water in the lower latitudes. So it tends to maintain the balance. That is known as heat balance. Next is rainfall. Now please remember the regions where the warm water is flowing, it tends to increase the temperature and it also increases the chance of water or rainfall happening. So it can basically help the region get more rainfall. Fishing. Newfoundland regions where the cold and the warm currents basically mix. Those are regions for very good quality fish, and fishing is one of the major economic aspects of that. So they are very useful for the fishing. Next is the climate. Again, climate is being impacted. We've already done that. Like for example, if the cold current is flowing along the coastal region, it might cause desert-like condition like the Patagonian desert. Now, it is also an outcome of the currents that are flowing, like the Peru current over here, or the Humboldt current is also influencing the Patagonian desert being present here. Yes, even the Falkland current is also present here. So On the other hand, if you realize that this region is not frozen during the time of winter, the coastal region. Why? Because of the warm North Atlantic drift that is flowing here. So that is why the climate is also influenced. Tropical cyclones, one of the preconditions that we had studied is existence of some low pressure. Low pressure is again brought by the warm currents also over here. So it basically helps in the creation of the ocean current or tropical cyclones. Last is navigation. When the ship or a water body is basically boat or a ship is flowing in the direction of the ocean currents, it basically consumes less fuel because it is moving in the direction of the ocean currents. So again helps in navigation also. Now let us see certain currents here. The red ones are the warm currents, the blue ones are the cold currents. Let us see the Atlantic Ocean here. If you see over here, this is North Equatorial Current. North Equatorial Current starts moving towards the northern part, and over here it forms a Gulf Stream. This Gulf Stream again is a warm current. It further moves upward in the form of North Atlantic Drift. This is basically important for keeping this region warm, as it takes the warm water from the lower latitudes to the upper latitudes. Now remember this. Similarly, in the southern region, you have a South Equatorial Current. This is a warm current which again encounters the Brazilian coast and starts moving downward. When it starts moving downward, over here it is known as the Brazilian current. Brazilian current. This is a warm current. Clear? Now please remember, this arrow which I have mentioned in the reverse order is quite interesting over here. This is flowing in the opposite direction. How come? The reason is, you have already understood that there is piling up of water along the coast of South America by the South Equatorial Current and the North Equatorial Current. So when it is piling up is done, so the water level raises, so there is a reverse current that flows which is in this opposite direction. This is known as a equatorial counter current. Equatorial counter current, right? Now please understand that this from the northern region over here, Labrador current comes. This Labrador current is again a very cold current because of the cold water that is coming, and this basically is one of the reasons why New York during the cold climate is completely frozen, the coasts are frozen during this time. Now over here, this is after from moving downward, some branch will move downward, and this is in the form of a little bit cold current which is known as a Canaries current. Later on it will again warm up and become a part of the North Atlantic current. If you come south over here, these currents that are flowing just in the southern ocean above the Antarctica, this is known as a west wind drift. Why it is flowing freely? Because there is no continent as such, so there is nothing to disturb them, so they are flowing. Some of them might just encounter the coast and turn upwards. This current is known as the Peru current. P-E-R-U, Peru current. Peru current, or it is also known as the Humboldt current. Peru current or Humboldt. Now this is one of the regions which makes this the western side as arid region with respect to South America because it is cold current. Similarly, some of the parts might move a little northward. This is known as the Falkland current. This is also a cold current. Now, on the other hand, when the Peru current moves upward, when it comes closer to the equator, it warms up. Then again, it is basically moves in the form of South Equatorial current over here. Again, North Equatorial current and a counter equatorial current flowing here, which you can see in this direction also, right? Now, over here, see, this is again, on the northern part, you have an Alaskan current. Alaskan current is a warm current. And there is a Californian current. This is a cold current along the coast of California. Now let us come to this region. Again, the west wind drift, some part might move upward. This is known as a Benguela current. This is again a cold current which causes aridity in the southern part of the Africa. Now if you come here, you will realize some currents will move a little bit northward. Again, West Australian current, which is again a cold current causing aridity here. This is again a South Equatorial current, and a equatorial counter current is flowing here, and an Agulhas current is flowing, which is an extended part of the South Equatorial current along with the coastal boundary of Africa. There is a Kuroshio current which is flowing as northward in the form of a warm current along the coast of Japan also, and there is another cold current coming from the north, that is Oyaishio current. So these are again the most important currents that you should know. If you know them, you can be very well use and understand them, how they are influencing the climate of a region also. Let us come to the topic of marine deposits. Now, marine deposits again are very important. We will be doing a lot of topics here. Ocean deposits. Now, ocean deposits, I'm just explaining you the chart right now, then we'll study one by one all of them, right? They're two broad categories. One is the terragenous deposit and other are the pelagic deposits. Terragenous deposits are divided into three categories: gravel, sand and mud. Mud is divided into further categories: blue mud, red mud, green mud, volcanic mud and coral mud. Then you come to the pelagic deposits. They are organic or inorganic in nature. When they are organic in nature, there are two types: calcareous and siliceous. Calcareous is generally found at not very much depth. That means less depth. Calcareous is present predominantly. As you move further in more depth region, or let us say deeper, you will find more siliceous deposits. Now, the calcareous has made up of two categories: petropod ooze and Globigerina ooze. Ooze is basically mud-like structure, mud-like formation, or which you will study right now also. So these are some form of mud. Siliceous can be diatomic ooze and radiolarian ooze. Inorganic are red clay. Red clay are the most dominant deposit that you can find in the ocean. Please remember that. We'll study now one by one. Let us see the terragenous deposits. Terragenous deposits are basically of continental origin. That means certain deposits or some erosion that took place on the continental surface, and they were again went through the form of certain erosional activities and went to the oceans or seas. So which in turn is an outcome of the weathering processes. That is why it is called terragenous material. So terragenous material is an outcome of the erosional activities that have taken place on the continents. Now gravel. Gravel has itself a wide variety, right from boulder, which has an average diameter of 256 millimeter, to even a granule which is less than 2 millimeter in diameter. Gravel can include boulders, cobble, pebbles and granules. The extreme form being boulder and the smallest one being granule. Below the gravel, you have the sand. Now, sand again can be very coarse to very fine, but again they are very small with respect to the diameter when you compare it with the gravel. Now, when you talk about silt, they are fine than sand. They are much more finer than the sand. When you talk about clay, they are finer than clay. When I'm talking about mud is even finer than clay. So as you move further, it is becoming more fine and fine. This is again very, very important here. Clear? Now let us categorize. Let us see, we have already done gravel, sand, silt and clay. Mud, which is finer than clay. But mud has to be studied because there are various categories of mud. Mud is of various categories. Now let us study one by one. This is not mentioned in the NCERT. Please remember that and make sure that you do it well. Why? Because this is something that can be asked in your examinations repeatedly. And I would request you to please go through this well, because when you go through this, you will be able to solve many questions which might be asked in your mains examination in particular, not only prelims. So blue mud, it includes material that is derived from the disintegration of rocks that are rich in iron sulfide and organic elements. The ones which are rich in iron sulfide and organic elements. Now, this forms blue mud, and now it has 35% of calcium carbonate. 35% of the calcium carbonate. Now, when we move ahead, there is red mud. Now, the red mud is derived from the volcanic rocks rich in iron oxide. It contains about 32% of calcium carbonate. Next is green mud. Now, green mud is basically it is formed due to the chemical reactions where chemical weathering, wherein the blue mud is changed to green because of the reaction of the seawater. And you will see that calcium carbonate over here can be from 0 to 56%. Volcanic mud. Now, these are because of the material derived from the surface and underwater deposits. Coral mud again are those muds which are because of an outcome of the depositions which is remained by the corals. So that is what is known as coral mud. Now, next comes pelagic. Now let us see what is here. We have done pelagic. Now pelagic has organic and inorganic and these categories. Let us study them. It consists of matter that is derived from algae and are mostly in the form of liquid mud. These are liquid mud-like composition which is known as ooze. Liquid mud is known as ooze, right? So these are mostly derived from again organic resources. First are calcareous ooze. Calcareous ooze has two categories, petropod ooze and globigerina ooze. Petropod ooze formed from a floating petrobod mollusk, again organic, right? Which is conical in shape. And that is why again you realize that these have large composition of calcium carbonate. So this ooze itself has 80% calcium carbonate. It is found at a depth of 300 to 1000 fathoms. 300 to 1000 fathoms. Then you have the globigerina ooze. Globigerina ooze. Now this is formed from the shell of variety of foraminifera. But most of the ooze is formed from certain germs. Those germs are called globigerina, and that is why this is known as globigerina ooze. Now this has calcium carbonate of close to 64% composition is calcium carbonate. Important thing over here is it lies between 2000 to 4000 fathoms depth, right? Next is siliceous ooze. Now siliceous ooze is also has two categories. That means greater amount of silica is present here. First is radiolarian ooze. It is formed from the shells of radiolaria and foraminifera. Silica over here is 5 to 20%. Lime content decreases as with depth. I had already told you with depth there is more of the silica content rather than the calcareous content. This is found between 2000 to 5000 fathoms. Second under the siliceous ooze is the diatomic ooze. Now they are formed from the shells of very microscopic plants containing silica in abundance. Now they are formed close to 600 to 2000 fathoms at the higher latitude. So these are because of the diatoms. Again, all of these are organic in nature. That is why it comes under the broad category of organic deposits. Now what comes under red clay is it is inorganic in nature. That is the last. It covers the largest area of the deep sea. It has silica of alumina, that is 85.3% oxides of iron, and it contains radioactive elements. If you see the deep sea plains or the abyssal plains, the largest area that is covered is of the red clay. So it is the major or the largest deposits. If anybody asks you, is the red clay. Please remember that. Next comes the categorization of marine organisms. There are a lot of marine organisms also present. You should be aware of that. First are the plankton community. So the planktons are again diverse group of buoyant and floating marine organisms. You know that very well that these are planktons which are floating on the surface of the water. They do not have their own strength like the fishes to move from one place to another. They're just lying or floating, and wherever the water takes them, they move. So extending up to 200 meters below the surface, they can be phytoplanktons, zooplanktons, algae, diatoms are present here. Next are the nekton community. Nekton community itself means swimmers. That means they're living organisms that can swim. So that means they're basically comprising the fishes which can move from one place to another, not merely dependent on the motion of the water, but their own strength to move from one place to another. So they move without being affected by the currents. Most of them are vertebrates and with various species of fish. Now, last is the benthos community. Now these are the ones which are lying on the surface of the ocean floor. Comprises all the plants and animals that are residing on the seabed. They can be seaweed, large algae, mollusk and oysters. Clear? Okay, mineral deposits. Now mineral deposits can be also of various categories which are found at various places. Some at the surface deposits. Now surface over here are basically talking about with respect to continental shelf and continental slopes. And then you have the bottom sea deposits. Please remember this. The minerals of the continental shelf can be zircon, monazite, magnetite, gold, platinum, sulfur, phosphate. Along with it, oil and gas resource are majorly found here. Here also oil and gas. So minerals of continental slope, cassiterite, that is type of tin, gold deposits, phosphorates, oil and gas are found here. Then you have the deep sea bottom deposits. Over here, manganese nodules are found here. Again, International Seabed Authority has also given the permission to India to explore manganese nodules. Again, they are very important for the industrial growth of the country also. Now, manganese nodules, polymagnetic nodule, these nodules containing various minerals like nickel, copper, cobalt, lead, zinc, iron, silicon are found. So these are very, very important, right? Polymetallic nodules are also present. Then you have the sea floor massive sulfides. Wherever there are hydrothermal ore deposits, you will realize that they are formed closer to the hydrothermal regions, and massive sulfide deposits are also found there. Right? They can be sometimes greenish to even yellowish, greenish to bluish color also. They are very often found. Right? Next is the conventional resources. Now see, conventional energy can include the petroleum and the oil natural gases that are found here. Non-conventional can be tidal energy, which can be used, wave energy can be used, or OTCE, ocean thermal energy conversion. This can also be used as a mean, but there is a very expensive method and limited scope. That is why it is generally avoided. Last comes the topic, which is the law of sea. Now please understand, this is a diagram that I've shown you. Now, I'm going to tell you certain things over here, concept of baseline, international water and all. Let's see something first of all before we move ahead. Have you seen very often that the coastline is not regular? Let us say it is like this. Now, how to measure the distance? How to measure the distance? Like we have seen over here, like they have said that territorial sea is 12 nautical miles. This is 12 nautical miles. How do you measure? Do you measure it from this region? How? What generally happens is, because the coastline is a natural form, so it cannot be of a defined shape. So what happens generally is, there is an imaginary line that is created, which is joining these pointed edges. Now this is known as the baseline. This part, which is inward, landward side, this is known as the, see here, this is known as the internal water. Clear? Internal water. So see here, this is internal water. Complete jurisdiction of the sovereign state lies here. Now this is something that you should understand. After this, it becomes easy, because baseline identification is something that is very difficult for a person who is just reading this structure over here, or this photograph over here. So now, what do we see here? Once you identified the baseline, it is based on just adding the pointed edges and just making a line. This is known as a baseline. From here, you calculate the distance, whether it is 12 nautical miles or so on and so forth. One which is inside this is the coast, and the water which is in the landward side, this is known as the internal water. Clear? Now let's see here. Baseline, it is the low water line along the coast as officially recognized by the coastal state. So this is the baseline, which is basically formed by adding or making an imaginary line through the projections of the coast. And this is known as a baseline, which is useful for further calculation of the territorial water and other features which you're going to study now. Internal water, the water on the landward side of the baseline. Landward side of the baseline, what do you mean by that? This is the baseline. Landward side is this. So this is what the internal water. Territorial sea. It extends seaward 12 nautical miles from the baseline. See here. This is the baseline. 12 nautical miles from the baseline is the territorial sea. Somewhat like, supposingly this is what? This is 12 nautical miles. 12 nautical miles. Now this is what is the territorial sea. Territorial sea. Clear? Now comes the contiguous zone. It extends seaward up to 24 miles from the baseline. It does not provide air or space rights. That means the other countries cannot fly simply their aircrafts over here, or they have to take permission, and they have to end before they enter this region also. So what is that? 24 miles. So let 12 miles is this, further 12 miles, that is 24 miles. This is what? This is the contiguous zone. Clear? Contiguous zone. Now comes exclusive economic zone. It extends from 200 nautical miles from the baseline. Now, if I want to extend this, please see this. From the baseline, this is 200 nautical miles. Right? This is what? 200 nautical miles. So this is the region is exclusive economic zone. Exclusive economic zone, but distance from the baseline is 200 nautical miles. So it does not give the coastal state the right to prohibit or limit freedom of navigation over flight. That means over this region, other commercial flights and commercial navigation can take place. It cannot restrict it. The sovereign state has right to carry out activities like energy. Over here, the whichever country has the exclusive economic zone, it can carry out its energy exploration with an exclusive right of its own. Then you have the high sea. Now beyond this, beyond the exclusive economic zone, till here it is exclusive economic zone. Beyond this is the high sea. Now over here it is for everybody. Everybody can move here, explore whatever they want to do. So this is again the law of the sea. So we have completed with the oceanography. Hopefully you enjoyed it. Hopefully you liked it. Hopefully you understood all the concepts that I've explained you. This is more than sufficient for your understanding for the civil services preparation, provided you do it well and you understand each and every factor that I've explained you with respect to the diagrams, concepts, examples, and the maps that I have made. Hopefully that was helpful to you. God bless you. Take care, and hopefully you enjoyed it. And please tell me how you like the lecture in the comment section. Take care and Jai Hind.